Hello again. Today we're going to be talking about compound events. Most of the unit we've been dealing with simple events. A compound event is made up of two or more simple events. Within compound events, we have two different kinds. The first that I'd like to talk about are mutually exclusive events. These are events that cannot simultaneously occur in the same experiment, or in the same trial of an experiment. So the formula that we use to find the probability of mutually exclusive events is the probability of A or B equals the probability of A plus the probability of B. Now this symbol, this U symbol, is going to be familiar to you because earlier this year when we were studying interval notation, we used it. For instance, let's say that we had a function which had a vertical asymptote at x equals 2, and it was defined on all the rest of the real numbers. In that situation, we would use this symbolism to describe the interval of the domain. Negative infinity up to 2, but not including 2, and 2 up to infinity. Now, what this OR here means is that any x value in the domain would either fall in this interval or in that interval. So we are using the same symbol to describe OR in a different context here. So for the example on your page, you have that Pepsi is running a prize contest on the caps of their bottles. Under each cap is labeled free Pepsi. Now we'll assume that that means a 20-ounce Pepsi. A free 2-liter or try again. There's a probability of 1 in 10 that a free Pepsi will appear and 1 in 25 that a free 2-liter will appear. Part A says explain why free Pepsi and free 2-liter are mutually exclusive. Well, let's go back to the definition of what it means to be mutually exclusive. The two events cannot simultaneously occur in the same trial of an experiment. So if you're doing an experiment with these Pepsi caps, you'd be twisting off a cap, looking and seeing what does it show. Now, we cannot possibly have both free Pepsi and free 2-liter underneath the same cap. Therefore, it can occur during the same trial of the experiment. Therefore, these two events are mutually exclusive. Next, what's the probability that a bottle cap is labeled free Pepsi or free 2-liter? So this is an either-or situation. Now we know that it's mutually exclusive from part A, so we can use this formula to find the probability of either free Pepsi or free 2-liter. We'd find the probability of free Pepsi and add to it the probability of free 2-liter. And that probability was 1 in 10 plus 1 in 25. Let's get common denominators. We could use 50 instead of 100, but I'll just use 100 here. So this would equal 14 over 100, or 7/50ths. Next, give me a moment and I'll get the next part of your notes set up. Inclusive events are events that have one or more outcomes in common. So the formula that we use for the probability of A or B when these are inclusive events is the probability of A plus the probability of B, take away the probability of A and B happening at the same time. Here's what this looks like in a Venn diagram form. Since these have one or more outcomes in common, I'm going to do an example where we have two outcomes that share some in common, or two events that have some outcomes in common. So A is here and B is there. So the probability of being either A or B would be the probability of being in either one or the other, possibly both, but at least one of the two. So in a sort of area sense, it would be landing in this zone that I outlined in red. Now, here's how we can make sense of this formula. Since we want to be in this red outlined area, we would take the probability of A plus the probability of B. But as you notice, if we just added probability of A and probability of B, we'd be adding this overlap region twice. We don't want to count it twice, we just want to count it once. So we're going to subtract off this overlap region once, and that would leave one of the overlaps remaining. That's why we subtract off this probability of A intersect B at the end of our formula. So then, with this example at the bottom of your page, we've got a deck of 52 cards. We want to find the probability of drawing a king or a heart. So this king or heart is an inclusive event. It's inclusive because it's possible to be both a king card and a heart card. And we know that there's going to be one of those cards in the deck. So we would know that one of these cards is either a king or a heart. Now, this zone here would be cards which are kings, but not hearts. So there would be 3 kings which are not hearts. So you've got 4 kings, 3 which are not hearts, 1 which are heart. Then for the hearts, we know there's going to be 13 hearts in the deck because hearts makes up a fourth of the deck of 52 cards. So it'd be 13 hearts, 1 of which is a king, and 12 of which are not. So then, to find the probability for part A using the Venn diagram, we would see that there are 3 plus 1 plus 12, 16 cards which qualify as either king or heart, 16 out of 52, giving us 8 out of 26, or 4/13. Now, if you don't really like drawing out diagrams for things, if you'd rather just use a formula, then here's how you would do it. The probability for part A of a king would be 4 out of 52. The probability of a heart is 13 out of 52. And the probability of being both king and heart is 1 out of 52. So to add or subtract fractions, we'll add the numerators. 17 minus 1, 16, which as we saw earlier, simplifies down to 4/13, giving us the same answer either way.